Hi all. Today we discuss theorem 11. Let m and n be positive integers, and let f be a field. Suppose W is the subspace of f cross n copies, and dimension of W less than or equal to m. Then there is precisely one m by n row reduced echelon matrix over f, which has W as its row space. That means corresponding to every subspace of dimension less than or equal to m, we can construct a row reduced echelon matrix of order m by n, such that this W is the row space. This is the theorem. So our intention is to construct a matrix with the row space of W. So the proof is there is at least one m by n row reduced echelon matrix with row space W. That is because once you are given a subspace W of Fn, then there exists a basis for this W. Say the dimension of W is equal to m. Then you can get a basis, say V, consisting of alpha 1 etc alpha m, is a basis for this W. Now you can easily consider, then this each alpha 1 is of the form alpha 1 is an element of Fn, so you can write it as some a11 etc a1 n. Okay, and similarly you can write alpha m as am1 etc amn. So now you can easily construct a matrix with these alpha 1 alpha 2 etc alpha m. So that is a11 etc a, this is a1n am1 etc amn. Okay, you can construct a matrix like this. Then the row space of this matrix, I call this matrix as A. Then row space of A coincides with the span of alpha 1 etc alpha n alpha m, that is equal to W. So once you are given a subspace, you can easily construct a matrix with a row space as W. That is always possible. Then you can reduce this A to this matrix A to a corresponding row reduced echelon form using the row transformations. So you can get at least then this row space of since this A is equivalent to R, the row space of R is same as this row space of A. So once you are given a subspace of Fn of dimension less than or equal to m, you can easily construct a row reduced echelon matrix whose row space is same as W. We need to so the existence of such a matrix is very easy. Now we will prove that such R is unique. That is the next idea. Here we have, since dimension of W less than or equal to m, we can select some m vectors alpha 1 alpha 2 alpha m in W which span V. That means if you the dimension of W is some R which is less than or equal to, which is strictly less than m, then you collect the rows alpha 1 etc alpha r first, then fill up with 0 rows to get this as n by n matrix. Okay, if this is R, then rest of the rows can be considered as a 0 rows. Then we can easily prove that this span of this alpha and alpha are the same as the span of the whole rows, that is equal to W. So the existence is very easy. Then this is the idea given here. Let A be a matrix with the row vectors alpha 1 alpha 2 alpha m, and let R be the row reduced echelon matrix which is row equivalent to A. Then the row space of R is W. Okay, so one such matrix R is always possible. Now we will prove that R is the only possible R is unique, a unique matrix from that vectors from the W. Now let R be any row reduced echelon matrix which has W as its row space. So we arbitrarily construct this R to prove that there is only one possible way to construct this R. For that, we consider rho 1, rho 2. If R is such a matrix, what are the importance of that R? Rho 1, rho 2, rho R be the non-zero row vectors of R, and suppose that leading non-zero entry of row I occurs in the kith column that we have already discussed in the previous class. The vectors rho 1, rho 2, rho R form a basis by theorem 10. Then we have this beta is equal to C1 rho 1 plus C2 rho 2 plus etc. CR rho R. Then we can easily conclude or prove that the Ci equal to Bki. This Bki is the kith component of the vector beta or the sum. So this beta can be written as, since if this happens, what is beta? Beta can be written as C1 rho 1 plus etc. CR rho R, but each Ci can be written as Bki. So this is Bk1 rho 1 plus etc. Bkr rho R. This shows that if this is beta, if we write this beta is equal to beta 1 etc. some in k1th entry we have bk1 etc. So these entries bk1 bk2, that means once you write this beta as b1 etc etc bk1 etc bk2 etc bkr etc bn. It contains exactly n components. So this shows that this is nothing but the summation I equal to 1 to r bki. Instead of ci we have bki rho I. Okay, so this shows that whenever we know these components, say bk1 bk2 bkr, then we can easily find this beta, or in order to know the details of beta or all the components of beta, we need only these components. Okay, we are not bothered about the other components. Okay, so this is the idea here. Any beta, if we consider a linear combination of this rho 1 rho 2 rho r and that is beta, then in order to define beta, we need only r quantities, r scalars in the positions k1th position, k2th position, etc., kth position. This is the importance of that row reduced echelon matrix. Okay, now thus any vector beta is determined if one knows the coordinates bk1, bk2, bk3, etc., bkr. For example, rho s is the unique vector in W which has kith coordinate 1 and kith coordinate 0 for I not equal to 0. This is kth coordinate. Kth coordinate is 1 and kith coordinate is 0 for I not equal to 0. Okay, so suppose beta is in W and beta not equal to 0, we claim that the first non-zero coordinate of beta occurs in one of the columns ks. Then this beta can be written as sigma I equal to 1 to or bk rho I as beta is equal to sigma equal to s to r, because the first non-zero entry comes under kth component, that is bks is the first non-zero quantity. bk1 bk2 are all 0. The first non-zero quantity is bks. So in this sum we can neglect all the terms before this bks. So any beta can be written in this form. From this condition 2.18, what is 2.18 here? That is the definition of this Rij. We have already discussed it in the previous class. Rij equal to 0 for I greater than s and j less than or equal to ks. Thus beta can be written as beta is equal to 0 0 0. Since the kth first non-zero entry comes under kth component, so 0 0 0 comma bks etc. bn. This is the general form, the form of a general vector beta in W. And the first non-zero coordinate of beta occurs in column ks. This is the first non-zero entry. Note also that for each k s equal to 1 to for each k s equal to 1 to etc. r, there exists a vector in W which has a non-zero kth coordinate, namely rho s. Okay, it is clear that from this onwards, these are the properties of which are the relation between the rows of row reduced echelon matrix and the W. Now we will construct R. Okay, how will you construct R? It is clear that R is uniquely determined by W. Okay, we will explain that in this way. The description of R in terms of W is as follows. We consider all vectors beta, beta 1, beta 2, beta n in W. If beta not equal to 0, then there exists, then the first non-zero coordinate of beta must occur in some column T. Okay, this column, the tth column is the this tth column contains the first non-zero entry of this beta. Then this bt not equal to 0. Let k1, k2, kr be those positive integers t such that there is some beta not equal to 0 in W. The first non-zero coordinate of which occurs in column T. Arrange k1, k2, that k2, etc., kr in order k1 less than k2 less than kr. That means once you consider W and choose a beta, okay, beta from W in such a way that when we choose this beta in W, we can get some of the columns at which the first non-zero entry occurs. This is BT, then all other entries are 0, and we have here non-zero entries anyway. This is Bn. Now how will you choose this? If once you got this beta 1, the fifth entry is non-zero, and other you can get the other way you can get some b2, another b2, beta 2 with non-zero entry in the third position. This is bt, but this is in the third position, etc. Then collect all such bi's, okay, beta 1, beta 2, etc., beta r. Then arrange this beta 1, beta 2 in such a way that, or in the ascending order of this. Okay, so if you have only 3 beta, then we have suppose we have last beta whose non-zero entry comes under row 5, row 6. Then we can arrange this in beta 2, beta 1, beta 3. Okay, this will give a matrix by arranging this, because in beta 2 the third one is the first non-zero entry, here the fifth one is first non-zero entry, here the sixth one is first non-zero entry. So arrange it in the ascending order. Then how will you choose this beta 1? Choose beta 1 in such a way that bt is equal to 1, and that means the fifth position is equal to 1, and the third position is equal to, from this you can say third, choose beta 2 in such a way that the third position is equal to 1, and fifth position and sixth position as 0 vector. Okay, choose a vector beta from W in such a way that whose third position is the first leading entry, that is 1, and fifth position is 0, sixth position is 0, and what will be the other entries. So choose such a beta from beta 2 from W, then make it as first row. Similarly, choose another beta 1 whose fifth entry is 1, and third entry and sixth entries are 0, and whatever be the next entries. Choose such a beta from W and call it as the second row. Similarly, choose beta whose sixth entry is 1, and all the entries are before this we have 0, and what will be the other entries, but collect this from W. Okay, this is the idea. For each positive integer ks, there will be one and only one vector rho s in W, such that the kth coordinate of rho s is 1, and the kith coordinates I not equal to s are 0. Okay, then this R is the m by n matrix which has row vectors, row 1 dot etc., row R, comma 0 0 0. So this makes R unique. Okay, so this is the idea. This proves Theorem 11.